guys, this is Edward from 413B, and this is a short video walkthrough tutorial on how to install pros for VEX V5 with LemLib, which is a library which has full support for Odometry and PID, which is what you would use in VEX Worlds, which is for the more advanced programming. So there's a tutorial on the LemLib documentation website, but this is just a video tutorial that's more in-depth, and I'll walk you through every step that you need to install it. So first, you want to go to Chrome and then search up Visual Studio Code. It'll take you to this website, and you want to click Download for Windows. And once you get the download, open it. It will run the installer, accept all the agreements, and go through the wizard. It will install Visual Studio Code for you. Once you have that installed, you want to open it. You want to go to the sidebar here where it says Extensions, and you want to search up Pros, and it's this first one here. You want to just go ahead and click Install. Once you install it, this message will pop up in the bottom right. If it doesn't pop up, close Visual Studio Code and then open it again, and it will pop up. It will say client toolchain are not working. You just want to click Install now. It'll install all the needed plugins that we need. Once it's done installing, it'll pop up with a little message there. I recommend just restarting Visual Studio Code just to be sure. Now, when we go back to Pros, we want to click Create Project, and then you can go to whatever folder you want and create a new folder. I'll just name this Pros Tutorial and then select folder, and then name your project. This will be what your program's called on your controller. I'll just name it Test Project. Select V5. You should say completed successfully. I recommend going with the latest, which is version 4, which they have good documentation for on their website. But version 3 is also fine, but I find that version 4 just has a little more added features, like for the free wire extender and such. Once we've created this project, you want to go to SRC, and you'll see we have main.cpp. We've finished installing Pros. Now we want to install LemLib into our Visual Studio Code here. You want to open the Pros integrated terminal. You can go back there, click integrated terminal, and it'll take you here. So you want to go to the LemLib documentation website. You can get here by just searching out LemLib, and then it's the second one that pops up. So install it. We want to install this other extension called ClangD. It will basically help LemLib compile everything. So we want to go back to Extensions tab on the side, and then search up ClangD, and then you can go ahead and install it. Once we have that, we can go back to our project here. We want to enter these two commands. So I'll copy this first one and enter it, and it will install LemLib and then install the latest version. There we go. Now we have the latest version of LemLib installed. I recommend going to their GitHub. It's the first thing that pops up when you search up LemLib, and if you scroll all the way down here, you can find an example project. So this has odometry and everything already integrated, and then what I would do is I just change all of the different values in here to fit yours. So I'll go ahead and paste this into main.cpp. So once we have this example project, I will walk you through all the different basic functions of LemLib. So this is where we set up our motors. So negative means inverse, so the motor will run backwards, and we want to set our gear set, which is what gear cartridge is in your motor. So make sure you don't mix these up, because we mixed them up once and it makes your PID go crazy. So this is our inertial sensor. I always recommend that you have one, because it is a very easy way to check the heading, and it's great for odometry. And this is just the port number that the inertial sensor is on. So after that, we have our two encoders. So we have, in this example, we have a horizontal and vertical, which is also what I recommend. And these are the ports that they're set on. And then we have the tracking wheels that the encoders are attached to. So this would be the diameter of your tracking wheel, of your Omni wheel. So this is using 2.75 inch Omni wheel, but we could also change it to 3.25, and everything would update. So this is the offset from our tracking center. Let's say that this is our drive base, and we have 4 wheels in each corner. So when we turn, our tracking center is going to be what point does not change when we like turn the robot. So in our case, this would be tracking center because it would stay the same when the robot turns. So let's add our encoders. You can place your encoders anywhere that is horizontal or perpendicular to the wheels. So like horizontal encoder here is valid. Also here would also be fine, or even here would be fine. So let's just say our horizontal is here and our vertical is here. Same for vertical, it can be here or here. Anywhere is fine as long as it is parallel with the drive wheels. And the offset that it is talking about there is actually this distance between the tracking center and the center of the wheel. So it would be this distance in inches for the vertical tracking wheel, and it would be this distance in inches for the horizontal tracking wheel. So that is what you want to put here. If it's on the back of the robot, you want to put negative. Forward, you want to put positive. So back, the offsets to the back, negative. Forward, positive. And if it's to the left, it's also negative. And if it's to the right, then it's also positive. So this is our drivetrain object. So we're basically just adding the motor groups that we defined up here. It's going to use those ports. And we also need to find our track width. Our track width is this distance, the distance between the center of your two side wheels. And this is the size of your drive wheels, which is different to the size of your Omni wheels. So these could be like 2.75 and these could be like 3.25, and you could still have that like as a valid tracking config, but you have to set it up in here. So this is the RPM that your wheels spin at. So this is dependent on your gearing. So we'll just leave it at 360 for now because that is a valid gearing. And horizontal drift basically tells your robot how fast it can turn. Let's say drift drive, if you have like 4 Omni wheels on the side, then you would want to put 2 because your robot could move sideways very easily. But let's say if we had like traction wheels here instead, we would want to put 8 because our robot cannot be pushed easily sideways, so we can turn faster. This is PID settings for linear motion, which is this way and this way for a normal drive base, and angular controller is for like turning like that. So you would want to tune these variables. So there is a flowchart which is very useful on the LemLib website here, PID tuning. You would want to follow this and the steps. I think this is a very good tutorial and it explains it better than I could explain it, especially this flowchart. So you would want to follow that. And once you have all that tuned, then we can proceed to the next step, which is setting up the odometry. So you can have 2 vertical tracking wheels, but in my experience, it doesn't really work well. So that could be used to track heading, but I recommend you just use the inertial sensor. It's much more accurate and it's very easy to implement. I recommend you have 1 vertical tracking wheel and 1 horizontal and 1 inertial. Horizontal will help calculate the swing, like if you're doing arcs or even if your robot gets pushed aside, that will be what is there to calculate it. So these are just some controller settings. I would just leave them as this. These are very good as is, but you can look more into it if you're interested in changing it. This is the chassis object, which is what we will be referencing every time you want to code something. So this just combines all of these that we defined up here. I think the default is very good. I'll just leave it as is. And then this is our initialize loop. So basically this runs before everything and it stops all of the other things from running. This will run first, and this just initializes your screen and calibrates the sensors. Just leave this as is. And then this basically puts a graphic on your screen which tells you where the robot thinks it is in X and Y and the heading that it thinks it's at. I think that this is very good for debugging, and this is also very, very useful for coding. So if you want to your robot to move to a certain point, you can actually just like use your hand and then drag the robot there, and it'll know which point it is. And if you just command it to go to that point which you dragged it to, it'll go exactly where you set it. So that's very useful for like quick programming. This is our autonomous loop. So this is the 15 seconds of autonomous that runs before every match. So if you have like in the competition template, this would be the 15-second autonomous. This is just some code which they've already written, but we'll just comment that out because you want to write your own, that's not going to work for anything. So there are 4 main functions that I love to use, which are very useful in my opinion. And there's also another algorithm called pure pursuit. Basically, you can set path that you want the robot to follow, and it will follow that path. It's very smooth, but it's also more advanced. I recommend starting out with just normal coding, which is what I do. So I'll show you how to do pure pursuit later, but that's what they use in like Worlds. So for normal functions, the most important would be move to point, in my opinion. Here. So it takes all these arguments, but you only need 3, but I recommend you use more. So I'll go through them one by one. So X coordinate, which is how far you want it to move in inches in the X direction. Y coordinate, I'll just set as 10 again. How far you want it to move in the Y direction. And then timeout, which is basically how long your robot will try to move there until it gives up on moving there, and it'll just move to the next one. I'll just set this as 1000 because it's in milliseconds, which is just 1 second. And then we have our extra parameters. We don't need these, but they're optional, but they're very useful. So let's say you want to grab a goal and you're in high stakes and your goal aligner is at the back. So you would want it to move backwards, but you need to tell your robot that, because if it doesn't know, it'll just turn around and then move there. So you want to put dot forwards equals false if we want to move backwards. Or let's say if we want to set a max speed, we would want to put dot max speed equals 80 or something like that. Or if we want to do half, it would be 64, because this value ranges between 0 and 127, which is max speed. So I'll just put it at max speed. It's already set as max speed by default. And you also have one more, which is async, which is basically whether, like, when it reaches the point, whether it should go on to the next one or whether it should just wait 1000 milliseconds. So if we put false, this command will always take 1000 milliseconds to run. But if we put true, which it is true by default, once it reaches 1010, it will go on to the next thing. So that is move to point. The next one, move to pose. So this is similar to move to point, but it also takes a heading. So it's everything's the same, except we have our robot down here. This is our robot, and we want it to move to the position here. Let's just say this is 1010 for demonstration. Move to point would basically just like find the fastest way to the position. So it would just move in a straight line and it would face this way, like just go to this point as fast as it could. But if you have move to pose, you can set a heading. So let's say it's heading 0 degrees right now. So theta would be 0. And we want it to move to 1010, 90. We want it to be facing that way. So what the robot would do is it would come up with its own fastest path to move to this point while facing that side. So that could be useful, very useful in your programming. That is the difference between move to point and move to pose. The next ones are turning based. So next one would be turn to heading. This basically just rotates your robot to the heading you want. Let's just say we want to go to 90. It also has the timeout like the other ones and the extra parameters, but I won't put that in. So this will just basically move the robot 90 degrees to and with a timeout of 1000. So the robot will just go from here to looking like this. It'll just go on the spot. So it'll just turn that side, this drive side forward, this drive side backwards, and it'll end up looking like that. So that is what turn to heading does. And there's also swing to heading, which is the same thing, except you can define a locked side instead of like moving on the spot. Let's say you want to swing to heading 90, your robot would swing, like one side would be locked and the other side would drive, and it basically just swings your robot to the desired position that you want. So like if we lock this side, it would just go like that instead of moving on the spot. But of course that also changes your XY coordinate, but it's very useful for aligning stuff like Mogomex. I use this a lot because the different sides are angled weirdly and it's much faster, and I'd say it's much more like reliable than turn heading. So I use this a lot. We can define the heading we want and also decide that it's locked. So I'll just put LemLib drive side, and then let's just say we want to lock left. That would be your command. It's basically telling your robot that this side is not allowed to move and only this side can move, and it would swing to 90. So the next thing is pure pursuit, which is basically if you want your robot to follow a path. Let's say you wanted your robot to go here, here, here. Pure pursuit, it follows a bunch of like dots that are set out on the path. This path can be broken down into a series of dots, and it will go to that dot and then that one next and then that one next and that one next and that one next. So this is very useful for like long paths that are very like fluid and dynamic. So to generate the path, you want to go to this website called Path Theory. Here, the first result. And this is already set up for high stakes. I've already played with this, as you can see, but you would want to change your format. This is the default. You want to change your format to LemLib V0.5. So right click to start path, and then let's say this is like where your robot's starting. This is like the finish point, or we can right click to add like extra waypoints. Let's say we want to pick up a Mogo goal before we go to donut, or we want to like pick up this donut first and then go there. We can all do that, and you can play around with this a lot. You can change the orientation of the robot at different locations, and you can also change like the max speed, like how fast or slow you want it to go in corners. It's very powerful. And you can also visualize your robot. If you put in the width and height, it'll create this box. This is basically the bounding box around your robot. So once we have this, we want to have these dots as a text file. So we want to put file, download as. I'll just put example file.jerryio.txt. Confirm. We want to go to our pro path directory. So where, remember when we created the project, where that folder is, and then we want to go into the main folder, and then static. This is where all your paths go. So we want to go back to main, and then we want to tell LemLib that this file here actually exists. So this is adding example. This is the example that they have. I'll just leave it there, but I'll just change this to be ours, which is example file.jerryio.txt. So now LemLib knows that this file is here. So once we've got that, we want to actually run it. So to use that, we use chassis.follow, and then this is the path that we want to follow, which is the path we just set out there. We'll just select it, and then look ahead is like basically the robot, like how far ahead it's gonna look in order to like compute the path. So it's in inches, so we'll just set like 10. It'll look 10 inches in front in terms of like how fast it's going. And the timeout for the path, we'll just set it as 1,000, which means it has 1,000 seconds to follow this path. And then we have all the extra parameters like we had in the other ones. So that is pure pursuit, and it will just follow that path if you have your PID tuned correctly. But if you're just starting out programming, I recommend that you use the turn to point functions and the 4 functions that I define in start. It is much easier to program with those. So this is driver control. This runs in the driver control period, the 1 minute 45 after the autonomous period runs in your competition template. So this is basically, this loop is just like updating your controller constantly. So you can even change this. This is set to arcade drive right now, but let's say you like tank drive, you can just change it to .tank and then put your left controller and then your right controller. Or if you want to play like inverted controls, if you like that for some reason, you can just put negative sign, but I wouldn't play around with this much because I like arcade drive. Yeah, that is where your joysticks are updated. So this is also where we would want to put our button code. So let's say that we want to spin a motor forward when we click R1. A simple way to do this would be just simple if statement, if controller dot get digital, because it is a button, and then R1. If we get that signal, then we want to move a motor forward. So how do we get a motor to move forward? So we can go all the way up to the top, and let's create a new comment, just say motors, and then we want to add a motor. So we'd select pros, motor, and then whatever motor we want. So my motor 1, and then the port it's on, let's just say it's on port 5. And if it's moving back, if it's like inverted, if we want to reverse it, we would just put a minus sign there. So that is our motor that we define. So if we go back down here, we can move the motor forward. If we can just reference my motor 1, and then dot move, and then 127. This is the maximum value to move it forward. And if we want it to go backwards, we put negative 127. If you want it to move at 50%, we just put 64, etc. You can also, up here, if you define like a gear set for the motor, you can also set it in RPM or like velocity percent, or even like voltage. You can set the voltage of the motor, but you can play around with that by yourself. What if we want to smooth pneumatic piston? We would go back up to the top, and we want to insert the libraries for pneumatics, which uses free wire ports. So we want to include pros/ADI. Okay, and then I'm gonna go ahead and make a new section for pneumatics, pros ADI, pneumatics. And then we can just go my piston 1, and then here we want to set our port. Let's just say it's on port A, and whether you want to start extended or retracted, let's just say we want to start retracted. So we just put false, and then that is our piston object. So we can go back down here and then go my piston 1 dot extend. That would extend our piston forward. Or we could even go my piston dot retract or something else. So this is just a simple button press, but what if we wanted like a toggle? If we wanted to code a toggle, this is just normal like C++. So we can just define like bool. Let's just say piston toggle equals false. Let's start as false. So once we have that, we'll just, when we're getting our digital signal, what do we do after we get the buttons pressed? Let's just nest an if statement, sorry. Let's just say if piston toggle false, then we will extend our piston. And then we'll set piston toggle to true. If the piston toggle is false, when the button is pressed, then it will extend and it will become true. If it's already true and it's already extended and the button is pressed, then you would want to retract it, right? So I would just put else and then my piston 1 dot retract and piston toggle equals false. So it would reset it. So if you clicked it again, it would go true. So when we get this button press, it will update every 10 milliseconds. So I would put like a delay command here so that when you press it, you have to like wait a certain amount of time before you can press it again, or else it'll just like retract and extend the piston like continuously for the period of the button press. So to do that, I would just go pros delay and I just say like 500 is enough, put on both. And now if you press it, it would toggle the piston on and off. So that's an easy way to set your buttons to toggle. And of course you can define multiple motors and multiple pneumatics, and you can even use like free wire ports for the encoders if you just use this instead of the port number, and you can use free wire expanders and have like LEDs. So I really think that Pros is a very versatile programming operating system for VEX. It's also very easy to upload to our robot. So if you plug in your controller or your brain, there will be a message that pops up which will say V5 controller connected. And once it's connected, you want to go ahead and save your projects, and then you want to click build and upload. That will build the project. So it'll compile all of this into a language that the VEX controller can understand. And then when you click upload, it'll upload it to your brain, but I don't have a brain plugged in right now. So you can also adjust your like project name and icon by going here to project.pros. You can change your name, description, program slot, icon, and this will be what is displayed on your brain screen when you upload it. So that's a short tutorial on how to set up Pros, basic project in Pros, and I hope you enjoyed, and thank you for watching.